Hello everybody, my name is Alex Tomsic. I'm the Director of Engineering for Red Wolf Reliability. This is the first in a series of videos that I'm putting together to talk about our Voyager FDS sensor. Specifically, this video is going to talk about the unit the sensor measures, which is strain. So this video was put together to provide some background on the purpose of the FDS sensor, as well as background knowledge on the unit of strain for those who may not have been exposed to it before. Over on the right side, you can see an image of the sensor itself. So this sensor is made to be mounted onto bearing housings for fluid film bearing machines, and it measures strain in the direction of the arrows shown on the top of the sensor. So the sensor was originally developed to monitor the health of unprotected fluid film bearings on turbo machinery. So over on the right side, you can see an image of the FDS sensor mounted, the blue arrows pointed to it. It's mounted to the face of a fluid film bearing on a large motor in a coal-fired power plant. So the FDS sensor monitors the health of these bearings through measuring the dynamic strain of the bearing housing due to the load of the rotating shaft. So for those of you who maybe haven't been exposed to what strain is in the past, you may have heard the term. So strain is typically denoted with the Greek letter epsilon, and it's a measure of a body's change in length compared to its original length in response to a load. So strain can be calculated from the equation shown in this image. So strain is the change in length divided by the original length. From that equation, you can see that the unit of strain is actually dimensionless. You're dividing a length divided by a length. So we typically will just denote strain with the symbol epsilon, since it has no real dimensions to speak of. So there's an example down below on this slide. So we have a tensile force that acts on a beam where the original length is 12 inches. Due to the applied force, the beam elongates to a length of 12¼ inches. So that gives us a change in length of 1/4 inch when loaded. So given this information, we can calculate the strain that the beam experiences by taking 1/4 inch divided by the original length of 12 inches, which gives us a strain of 0.21 strain. So the animation is from a finite element model, just displaying the same idea of a beam loaded in tension. So you can see as it loops through, the beam starts at a fixed length, and as that load is applied, it elongates to a certain extent. This elongation is what's going to cause the strain in this beam. The same relationship is true for a beam that's loaded in compression. The main difference is the beam actually experiences a negative strain because the change in length is negative. So now if we think about what the main purpose of the sensor is, the same is true for a bearing. If you apply a load to a bearing, that load from the shaft is transmitted through the bearing or to the bearing by the high pressure oil, and the bearing housing experiences a correlated strain. So as you can see in the image below, this is actually the strain profile that you may see on a bearing housing under a compressive load at the bottom. And you can see that the light green portion is actually where the high strain exists. And so if we were to measure strain on this bearing housing, we'd want to be in that region where the light green exists. One important thing to remember about this is that all of the strains talked about in this video are static strains. So we're applying a fixed load to the body, and we're just experiencing a fixed strain because of it. Now, the FDS sensor, and what we'll be talking about in the next video, is what are dynamic strains. So the FDS sensor itself will only measure dynamic strains. It's not designed to measure static strains. Thank you.